So today we will do a very important set of sample spaces, or a concept you can call it. Our title is at equally likely outcomes. So here the idea is that you have a sample space. Let's say it consists. Let's say S is sample space, and S is countable. That is, you can count the elements in S. Let's say it's countable collection. You can think of it as a finite set or some index by natural numbers. So one important feature is it is enough to describe the probability of each outcome in S to describe the probability of all events. So by this I mean the following: that let's suppose I know probability of omega. I know this is known for all omega in S. Suppose that. Then if you look at any event A is subset of S, A is an event, then the probability of A, you can write it first as the probability of union of all omega in A of the sets omega. Now this is either a disjoint union of countable sets, disjoint union, and I just write as countable disjoint union because S is countable and A is subset of S. This is equal to now the sum over omega in A, the probability of omega, by the axiom 2 of probability. This is, I'm using axiom 2. So now you notice that the moment I know probability of every single outcome, I know the probability of the event. So in some sense, the assignments of probability of each outcome give sort of a kind of a weight for every outcome, which we'll describe as the distribution. So this is a special term that people use all the time. The assignment of probabilities to each outcome is called a distribution. A distribution on it's called distribution on S. So this is a distribution on S means it describes how probability is assigned to each outcome. So in the countable setting itself, in the generality this is true, but the most interesting case occurs in interesting and understandable case is when S is finite. And here there's sort of a unique feature. So let's take two examples. Come back to the examples again later on. That makes sense. So let's take one example. Let's say as an example. So one is that let's say we toss a fair coin. This is an experiment in which S is heads and tails. And we already saw that the probability of heads in this case was equal to probability of tails was equal to 1. So here was a setup when S was finite, tossing of a fair coin, it means that heads and tails were equal likely to apply, and that gave you the probability of heads equal to half and tails equal to half. So just to rephrase this sort of this example that we did before, so this is a case in which S, the outcomes in S were all equally likely. That is, every outcome is half. Probability is half. There are two outcomes, each comes probability. This phenomenon is a little bit more general. For example, let's go to the other example. Let's say we roll a fair die. Right? So the outcome is just so S will be 1, 2, 3, 4, 5, and 6. And then we can verify, one can verify that the probability of any single outcome is actually 1/6. Is 1/6 for all k in S. So then again, an experiment where we see that the probability of any single outcome is the same as any other outcome in the sample space. So this phenomenon is a little general in that sense. So we'll try and place this phenomenon in a general setup when S is any terms of n elements, where n is arbitrary. So I'll write in the form of a theorem. So here's the theorem. So I'll call it 1.2.1. And the distribution, or the way I assign probabilities to this set, is called uniform of omega 1, omega 2, up to omega n. Okay. So that's what the theorem is going to do. So the idea is that you let S be finitely many elements, omega 1, omega 2, up to omega n elements. So this will be a non-empty finite set. Then if E is a subset of S, let the probability of E to be equal to the number of elements in E divided by the number of elements in S. The same as the number of elements in E divided by n. So let's say where mod E is the number of elements in the set E. So that's how I'm going to define a probability. Okay. Then the conclusion is so E is this, let this vector be this. Then the conclusion is that let me stop here. Then the conclusion is that P defines a probability on S. Probability on S. And more importantly, the crucial thing is that P assigns equal probability to every individual outcome of S. P assigns equal probability to every individual outcome in S. So it's a very crucial one. So let me do the proof of this. So what do I mean by this? The theorem, let's just, before I write the proof, let me explain the theorem again. So, see, I have a sample space S. And what I do is, I have the event space, this is a set of all subsets of S. So for every subset of S, I assign the probability of E to be the number of elements of E divided by n, where n is the total elements in S. Number of elements in S. Now the claim is that this definition automatically ensures two things, that P is indeed a probability on S. Let me make it cleaner. And Moreover, P assigns equal probability to every individual outcome. So let's try and see how to prove this idea. So to show P is a probability on S, what all I have to verify? I have to verify first P is indeed a function from 0, 1 to P is indeed a function from F to 0, 1. I have verified this, right? So is this true? Let's verify this. This is true. This is indeed true. True, as E is subset of S will imply the number of elements of E is always non-negative, it could be empty to 0, is less than equal to the number of elements of S. So which implies that by definition P of E, which is equal to mod E by mod S, which is equal to N, is in fact an element of 0, 1. It's a number between 0 and 1. Because if I divide E by S, mod S was equal to N, right? So we that the mod S was the same as N. So if I divide E by mod S, I get a number between 0 and 1. So P is indeed a good, well-defined function. So P is a well-defined function. So the first claim is that P is a well-defined function. The second thing is, I have to ensure the two axioms of probability. So let's verify axiom 1. Okay. So let's call this as step 1. Step 1 is to verify it's a function. Step 2 is to verify axiom 1. What does axiom 1 say? Axiom 1 says the probability of S should be 1. But what is probability of S? Probability of S by definition is mod S by N. Because that's what the definition of any subset S is, size of E by size of S. So mod S by N, which is same as N by N, which is equal to 1. Very good. So indeed it's verified. So therefore, axiom 1 holds for this function. Step 3, what is step 3? Step 3 is I have to verify axiom 2. I have to verify axiom 2. So how do I verify axiom 2? Axiom 2 you can verify in the following way, right? You have to take a countable sequence of events. So let's say E1, E2, and so on and so forth, and En, so on and so forth, are a countable sequence of disjoint events. So perhaps I should say let E1, E2, En be a countable sequence. This is given to us. So now we observe little s is finite. Mod s is finite. So s is finite. S is finite. And mod s is equal to n. So capital mod s has only n elements. So in some sense, if I have a countable sequence of disjoint events, they have no intersection, then after a while they all have to be empty because I would have exhausted all the elements in S. So this is a small exercise to think about. We may assume without loss of generality, that is, we can rearrange the EIs in suitable form. Generality that only the first n elements are non-empty. That is, E sub j is empty for j bigger than n. So this is you have to just do it by just rearranging EJs. Because you can only have at most n disjoint events in S, non-empty ones. Otherwise, you'll have empty ones. Right. And you also observe this following fact. So now, once you have this, you know that size of E1, E2, union En, if they're disjoint, is the same as the sum from j equal to 1 to n modulus of Ej. That's just a fact if the sets are disjoint. if you have disjoint events, disjoint sets, if you add them up, the size adds up. So if you take the union and take the size, it's the same as adding the size of each. So now let's go to our proof now. What do you have to do now? You have to. These are the remarks you have. This is one important remark, and this is one important. So now what you have to do? You take the probability of the union j equal to 1 to infinity e sub j. So what's that going to be? That's going to be again. So e sub j is empty after n. So that means this is the same as probability union j equal to 1 to n e sub j. So let me call this as maybe some number. Let's call this star prime. This is by star prime, right? Because after some time everybody's in. Now we know this is by definition. What is it? It is the size of the union j equal to 1 to n e sub j divided by n. Right? But by this other fact, let's call this star double prime now. So what do I get? Star double prime will imply that I get this is the sum of the EJs, sum of the size of EJs, modulus of EJs divided by n. But lo and behold, this guy essentially is equal to the sum j equal to 1 to n probability of EJ. But now, because probability EJ is just size of EJ by n. But now use the fact that again use star prime and the fact that probability of an empty set is 0. Use both these facts to get this is the same as summation j equal to 1 to infinity probability of EJ. Because after n, everybody is empty, their probability is 0, I can throw them in. So essentially I have verified axiom 2. This implies axiom 2 is verified. 2 is verified. Very nice. Very good. So that means what have I done? I have verified that this function defined in this manner, this probability of E equal to size of E by size of S, is in fact a probability. That it's well defined, it verifies axiom 1 and verifies axiom 2. We'll come back and review the proof in a second. But what is left? I have to show it assigns equal probability to every outcome. That's quite easy. Let's see why is that easy? Let me just go back down. So last step is to verify that let's do step 4. So I'll just call it the equally likely outcomes distribution. So how do I verify this? I have to take the probability of, let's say omega is in S, some element in S. Probability of omega by definition is what? The size of omega divided by n. But size of omega is just 1. So it's 1 by n. So that means this is the same for every omega. So it's same for any omega. That means we verified the fact that every outcome has the same probability. So each outcome in S has the same probability, but I write it as each outcome is equally likely. Because they all have the probability 1 over. So it's a very important, nice theorem. So let's go back, and since I want to stress this on this a little bit, let me go back and redo this proof to you in one summary shot. So the idea was that I wanted to come here, very nice, let's think here, step 1, step 2, step 3, very good. So the idea was that I wanted to imitate this idea that I have a toss of a coin, a fair coin, probability any outcome is equal likely because probability heads is half and tail also is half. Similarly, if you roll a fair die, the chance that each outcome is 1 over 6, you can verify that. So then that motivated us to define it in a little more general manner. That's called the uniform distribution on n elements. So omega 1 through omega n. So what you do is you define the size of any element E as the number of elements E in that set. And then you define the probability of any event E as the size of E divided by n. And once you've done this, you look at this. I can claim that P defines the probability on S, and P assigns equal probability to every individual outcome. Right? So further, what you have to verify? You have to verify that this definition indeed defines the probability. So what I did was I took the map P from the event space to 0, 1. I had to show it's a well-defined function. But this is indeed true because you take a subset of E, the number of elements in E is going to be less than the number of elements in S because E is subset of S. That means probability of E is probability of size of E by n, which is a number between 0 and 1. So 1 is verified. To verify axiom 1 of probability, I have to verify probability of S is equal to 1. But that's also easy because S probability of S is size of S by n, which is n by n, which is equal to 1. So axiom 1 holds. Now verify axiom 2 the same way. Let E1 through En be a countable sequence of disjoint events. S is finite. Size of S is n. Then the crucial thing is that if you have n elements in S and you have a collection of disjoint events, after some time they have to be empty. So you can rearrange them. So the first n elements are at most non-empty, but everybody above that is empty. That's what star prime does. The star double prime just does a simple fact. If you have n disjoint events, the union size of the union is the size of the sum of each size. That's what second one does. Once you have this, you just have to observe that the countable union first reduces to the finite union because everybody is empty after some time. And the probability of finite union is defined as the size of the finite union divided by n. But that by star double prime is same as the sum of the size of this by n. But lo and behold, size of Ej by n is same as probability of Ej. And that implies that the sum of j equal to 1 to probability of j is the same as the countable sum. So axiom 2 is verified. Once axiom 2 is verified, equilaterally outcome distribution is also automatic because probability omega is size of omega by n, which is 1 over n. So it means I have verified both these statements. The P is a probability by the first 3 steps, and the fourth step tells me that probability of every outcome is 1 over n, the same outcome. Very nice. It's a very important idea. This is called the uniform distribution on n elements. And the way you define it is that you define it by the size of the set divided by n, by the total number of elements in sample space. Very good. Okay, good. Okay. Now let me do a couple of examples to sort of set this notion correctly, and I'll close this discussion. Very good. So here's an example. Example 1.2. So let's say I have two dice are rolled, and I want to know how likely is their sum will equal 8. Okay? 2 dice are rolled. And I want to know how likely is it that their sum, how likely is it that their sum is equal to 8, will equal 8. Is that clear? The idea is clear. I roll 2 dice, and let's assume they're fair die. 2 fair die are rolled, and I want to know. So there are various ways of setting this up. So let's do method 1. So method 1, you could say, okay, fine. I have 2 rolls. I'm rolling 2 dice. I'm interested in the sum. So the sample space S will be the sum of the two dice. What are the possibilities of sum? Both are 1, 1, it's 2, 1, 2 is 3, and so on and so forth. Up to both are 6, 6, I get 12. So this is a sample space possibility. This is a sample space possibility. And then you'd say, it's okay, fine. Now I'd like to compare and find the probabilities of each outcome. But this turns out a little hard. It turns out that once you do it like this, it turns out it is a bit harder to assign probabilities. In the sense that you have to think a little bit, what are the possibilities that will give you 3 and how likely each is, and so on and so forth. And it is definitely not the case that all outcomes are equally likely. And it is not the case that all outcomes are equally likely. So instead, I do it like this. I think of it, I don't do it this method, I abandon this method. I do the next method, method 2. So in this method, what I do is, I say, fine, I don't think of it as observing the sum. I think of it as rolling one die, rolling another die, noting the outcome, and then I compute the sum that I want. Okay? So what I do is, I view the experiment as rolling a die, one die, and rolling another die. So then the sample space S becomes, so the first outcome could be 1, the second one could be 1, then 1, 2, 1, 3, 1, 4, 1, 5, and then 1, 6. Okay? Then you go all the way down, you get 6, 1, and then all the way to get 2, 1, and so on, 6, 1, and then 6, 1, 6, 2, and then 6, 6. And here you have 2, 6, 3, 6, and so on and so forth, and you have 2, 2, and so on and so forth. This is what you do. So that means you list out all possible outcomes that can occur in the two rolls, or one dice and second dice. Now you know that if you roll a die, each outcome is equally likely. That means any one of these points in the sample space is equally likely. So now we are in this. So any outcome in S is equally likely. So that's something you observe immediately. So now that means I can use my previous theorem, right? So that means the size of S is what? 6 possibilities in the first guy, 6 in the second guy. So size of S is 36. And equal likely experiment. Then we know from this theorem that we did just now, this theorem 1.2.1, that, so let me write down that in the room so that it's clear. So theorem 1.2.1 in maroon, that the size of E is going to be, probability of E is going to be size of E divided by 36, right? That's what's going to give you. Very good. So if you want to define a probability on this S, it has to be the size of E by 36. But now what are we interested in? We are interested in the event that the sum will be equal to 8. So let's write the event down. What's the event E? The event E is sum of the rolls equals 8. But sum of the rolls equals 8 means what? That means if the first guy is 1, then I can't get 8 because the highest is 6 for second guy, 1 plus 6 is 7. So I'll have to start with 2. So first guy is 2, the second guy can be 6. There's no other choice. So once I get the first guy, the second guy is 6. The next is, the first guy is 3, the second guy has to be 5. The next is 4, 4, 4. And then I can go bigger, I go 5, and then 3, and then 6, and then 2. So these are all the outcomes that will give me the sum is 8. That means, and also know immediately that the size of E is what? Is 1, 2, 3, 4, 5. Size of E is 5. That means the probability of E is equal to the size of E divided by 36, which is 5. And if I do a little jugglery, let me move this around. So this. Oops, sorry about that. Okay, I'm not good at this. Let's see. I'll try one last time. One more time. Very good. We move across. So now I'll just erase this part right here. So what I wanted to say was that the probability that the sum equals 8 is the same as the probability of E, the size of E by 36, 5 by 36. So you have, so what the point of the exercise is the following, that you have to be a little bit sort of careful. When you're given a question, if you want to use the previous theorem, you have to set up the problem correctly. If you go method 1, you're going to be a little bit stuck a little bit. Okay, I don't know what to do, what's going on. I know that's in probabilities and so on. But once you set up like an equal likely experiment, then the challenge then becomes quite simple. All you have to do is make sure you identify the event E correctly. That's some of those. Okay. So just quickly recall the whole setup that we did today. One was that the whole point was how to throw a uniform distribution on n elements. And the way one does that is that you assign the probability in the event E as the size of the event E divided by mod S. And then this theorem shows that this defines a probability on E, probability on S, and assigns equal probability every outcome. Then this example tells you that if you want to apply this theorem, you have to be a little bit careful. You just have to make sure that you set up the experiment correctly. In method 2, I set it up so that S had a set of outcomes where each outcome came equal likely in my experiment. And that implies that the size of E divided by total number of elements determines the probability of E. Once I have that, I identified my event E as a sum of the rows of equals 8, which is equal to 6, 2, 6, 3, 5, 4, 4, 5, 3, and 6, 2. And that gave me the answer. Very nice.